Hello friends, welcome to follow up. Let's continue our plan and look at problem 684, redundant connection. So in a previous video, we presented two formats of solutions based on unified. So in this video, we are going to present two formats of solutions based on traversal. So again, let me briefly recall this problem. So here we are given a undirected graph. So we want to make this graph a tree by inspecting the extra edge, right? So this is the problem statement. So here we want to return an edge that can be removed so that the resulting graph is a tree of n nodes. And if there are multiple answers, we want to return the answer that occurs last in the output. So here I want to point one point in the constraint, that is the size of the problem. So here n is bounded above by 1000. So n is the number of nodes. So with that said, let's look at the coding part. So here, one of the reasons we present a solution based on traversal is the following. So we want to present some method which is used to determine if a graph is a tree, right? So notice that a tree is a connected graph with n-1 edges, where n is the number of nodes. So with that said, let's first look at the coding. So here I want to first get a hyperfunction, that is, if it's a tree. So here, given L is a list of edges, right? So for this, first let's define a graph. Let's say collections default dictionary. So we're going to use list, or you can use site. So both are okay. So let's use site. And then basically let's first build the graph, use the L. So for UV in L, right? So graph U at V, because V is in the neighbor, is a neighbor of U. So similarly, because here we consider undirected graph, right, or bidirectional graph. Let's do this. Grad V, GV at U, because U is also a neighbor of V. So it's actually very important to notice for this problem, we are dealing with undirected graph or bidirected graph. So with that said, in order to check if this is a tree, we want to start from any of the nodes. Let's do this. Let's use a queue. Let's see. I can use a deck, collections and deck. So though I use deck, actually the behavior I want to use is the queue behavior, right? So we can get one key. Let's see, list of G. Let's see, keys, right? So we just take this first one. Let's see, and then let's see visited. So this is help us for visiting. So this node 0. So for node in G. So originally all these nodes are untouched, right? So we want to do traversal to check if there is a contradiction, right? So in other words, the return is a boolean, telling us if the graph based on this L is a tree or not. So the traversal actually is rather straightforward. So we have Q. So let's see, current node is Q pop left. So once we pop this one, this is a node we are currently visiting. So we are going to say visited. So we set it to be positive one. So notice that this is important. So when you can regard this is the number of visited node, or you can see in this while loop, it's a node we are currently visiting. The importance of this is induced from the fact that we are dealing with bidirectional graph. It's very crucial. If we are dealing with a directed graph, we don't need to pay too much attention here. So now with that said, let's check the neighbor. For neighbor in graph current, right? So if visited, if the neighbor corresponding to a value -1, so then we are going to return false. So why it's going to give us false, you'll see as we look at the next if not visited neighbor. So if the node haven't been visited yet, so we can append this neighbor. And also after we appended that, we are going to set visited the neighbor to be -1. So we can understand that 1 means visited, or in this loop is visiting, and -1 is the node to be visited, right? So then if in this first check, if you see neighbor is a node to be visited, so we are going to return false. So if we see to be visited or visited is relative concept, right? You need to digest this point. So now if haven't returned in between, we need to find a last layer of check. So we want to check if all the nodes are visited. So we are going to check sum g of visited, so values, right? So if all the values are 1, so this will equal to the length of this graph. So this is the main hyper function. So now with this function in at hand, we are going to do the problem logic. So because we want to find the last one, return the answer that occurs last in the input. So what we are going to do is to use the reverse order. So for IDX in reversed, let's reverse range length of this edges, right? Then the current, we can consider delete this current edge. If this, after we delete this current edge, it still give us a tree, a valid tree. Then this edge is the edge we are going to remove, right? So let's see, edges, new, edges, delete 1. So this is going to be edges. So we are going to up to this one, and then edges. So IDX plus 1 onwards, right? So then if edges, so let's see, if this is not empty, right? And this also gives us a valid tree. So in this case, what we want to do, so let's see, this is tree, right? This is the edges. So we're going to return edges IDX. So due to the problem assumption, we will always get something, right? So this actually forms a solution format. So I guess we need to first do a test, and then we come back to explain this check function again. In other words, if it's a tree. So now let's do a test. Yeah, it passes the first example. So now let's look at the generic case. Yeah, it passes all the generic cases. So here we are going to have 2 comments. The first one is related to the size of the problem. So here actually we do a lot of, we call n times this function is tree, because if we in general, so if we at the very beginning we meet this, so we are directly returned, right? So essentially in practice we will not call exactly n times if the n is the length of the edges, right? So this is the one thing. And another thing is that how do we understand this one? So here we have +1, we have -1, and initially 0. So in order to digest this part, so you can consider this example. So you can consider example just 2 nodes. Let's see, we have node 1. Let's see, let's use node A and then node B, right? So then this is just one edge. This is the valid tree. So how do we do this? So for example, A is in the neighbor of B. The graph is something like this. A corresponding to a set B, right? And B corresponding to a set A. So now if we have a queue, let's use A as a demonstration. So then if the visited, so we originally we have A is 0, B is 0. Both nodes are not touched yet. And then we look at Q. So first we pop, so we are going to get the current is A, right? So now the queue will be empty. So once we do this, we're going to set A to be 1, which this will be 1, right? And then we look at the neighbor. So A have a neighbor that is B, right? So in this case, B is not -1, and B actually is corresponding to a value 0. So B is not visited. So we are going to enqueue this B. So we are going to enqueue this B, and also we are going to change visited B to be -1, right? And then we are going to look at the queue pop. So we are going to get B, and the queue will be empty. So now, because B originally is -1, so now if we look at this visited, we're going to set visited B to be 1, right? So this is the crucial point. And then we check the neighbor. So the neighbor for B is A, right? Because A is 1, not -1. So there's nothing returned. So later we see that both A and B are visited. We are going to have 2, but we have 2 nodes, so we are going to return true. This is indeed a tree, right? So basically, I hope that this quick digest help you understand the way of 1 and -1. The overall reason is that we are dealing with bidirectional graph. So this is important. So this is the first version of solution. So now we are going to look at the second version of solution. Still based on traversal, but we want to use a traditional format of traversal. That might be useful for some people. So here, I want to check, if 2 nodes are connected, right? Because in a tree, there is a path between any 2 nodes. So that's our starting point. So here again, I'm going to write a hyperfunction. That's also one of the reasons, because for these two formats of solutions based on traversal, our main focus actually is on the hyperfunction. So this hyperfunction is crucial to know. And also it can be used to solve or address other problems. So here, let's do a breadth search for node 1 and node 2. So if it's in a tree, we actually should expect there's a path, right? So here we are going to return Boolean. So here we have a queue. Let's start from node 1, right? So then we use a visited. This will help us to avoid a repetition. So we're going to have a set, and then that's a standard while loop, right? While queue. So the current node, so it's going to be queue pop. So here pop 0, but if you use this collections deck, so you can use pop left. But for this problem set, pop 0 will be fine. Let's use pop left. And then we want to check if current equals node 2. In other words, current equals the destination. So we're going to return true. It means that there's a valid path between these 2 nodes. And otherwise, so we're going to look at the neighbor of this this node. So for the neighbor in graph, let's do this. Let's see, we check all the neighbors for I in range. So let's see, length, the corresponding graph. So we are going to build a graph. So the graph current node. So current. So what we want to do is check the node. So the node will be let's do this. Let's maybe for neighbor in graph current, right? So if neighbor not in visited, so what we are going to do is going to append this neighbor. So here actually, because here we didn't add, so we can still here add this part. So we can do visited add node. So or we can do here. So let's do here, visited add current, right? So then what we are going to do, we are going to return. So if we didn't arrive at node 2, we are going to return false. So that's a short function for checking this relation. So next, we're going to incorporate the current problem logic. So for this, let's first build the graph. So that's why you see we have a graph here. The graph is collections. So we're going to use default dict. So we're going to use set. And what we want to do is to for check, right? For node 1, node 2 in edges. So before we add those two, node 1 to node 2, there should be no connections between the two nodes. So if we call this BFS function, we expect it return false, right? But if it returns true, means that node 1 and node 2 gives us a redundant edge. So basically what we want to do, if node 1 in graph and node 2 in graph and BFS, node 1, node 2. This means these two nodes have a redundant edge. So we're going to return node 1 and node 2, right? So otherwise, what we want to do is graph. So we have node 1. So we need to add to node 2 because node 2 is in the neighbor. Similarly, graph node 2. So add node 1, right? So due to the way of the assumptions, so this will return an edge for sure. So with that said, let's change the, we have already changed the nature function signature. So now let's do a test. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases. So here I would say for these two formats of solutions based on traversal, it's actually the main part is the two hyperfunctions here. In this first one, we implement a function to check if a bidirectional graph is a tree or not. So this is of general interest. In the second one, it's rather routine. So here, given two nodes, one is a source called node 1, and the other is a destination. We want to check if there is a path or if the two nodes are connected. And then, due to the way of the problem in the second format, we iterate from beginning to end. And before we do the add operations, and then the two nodes should have no connection. If there were connections, this means they produce redundant edge. So that's the logic for the second version. So I would say these two formats, we can do that. Here is more or less due to the assumption that the problem set is bounded above by 1000. For this current video, we used the traversal-based solution, while in the previous video, we used a union find method. I guess for this problem, I prefer the former. In other words, the union find method. But to digest the problem, in the series of two videos, we present both union find method and the traversal method. Hopefully, it will be useful for some people. With that said, you are welcome to follow up our other videos or our playlist. Thank you.